Hi there, welcome to this lecture series on matrix algebra. This is lecture 32, part 2. In this lecture, we'll continue our study on applications of matrix algebra. In particular, we will look at various functions of a matrix. Let's get started. Let's review what we have already learned on polynomial functions of a matrix. So given a matrix, a square matrix A, n by n, we can define its powers as follows. So a to the power 0 will be the identity matrix. A to the power 1 will be A, and a to the power k, when k is bigger than 1, will be just a times a times a k times. And then for every polynomial p of t, let's say t is a scalar number, this is defined as a constant ck times t to the power k, and summing over k from k equals 0 to m. And a function like this, and the equivalent version with the matrix as the variable would be p of a, and there would be the summing over k from 0 to m of ck times matrix A to the power k, where matrix A to the power k is defined above. So we are asking the question, what about other functions? We want to be able to define more functions of a matrix beyond just that. So for example, exponential or square root, these are the two examples that we'll be talking about. Let's first look at functions of a diagonal matrix, which is always way simpler to understand. So consider we have a diagonal matrix, which has lambda 1, lambda 2, lambda n on the diagonal. Then if you take it to the power k, that is d times d times dk times, and it's easy to verify that. It's also a diagonal matrix, and along the diagonal, you will simply have the kth power of the original lambda, the diagonal. So it will be lambda 1 to the power k, lambda 2 to the power k, and all the way to lambda n to the power k. Once we have that, we can now define the polynomial function for a diagonal matrix rather simply. So p of d corresponding to this polynomial would be the summation of k from 0 to m ck times d to the power k. And we can put in the d to the power k, which is this diagonal matrix, and we'll be summing over that. And then we can further manipulate. We can multiply the scalar number into all the diagonals, and then we can move the summation sign into all the diagonals. And it is actually summing over everything, but all these are zeros, so you sum them up, they're 0. So the only non-zero terms will be along the diagonal, and they take exactly these forms. And then we recognize that a summation like this is exactly polynomial of lambda 1, so p of lambda 1, and that's p of lambda 2, and that will be p of lambda n. So this becomes again a diagonal matrix where the diagonals will be the same polynomial function p of the lambda i's along the diagonal. So in the same way, we can now define exponential of a diagonal matrix. We will be using the Taylor series. So we define e to the matrix d to be the same Taylor series, where d becomes the independent variable. So we have that. So summing over k of 1 over k factorial d to the power k. So put it in the d to the k, which is this diagonal matrix here from previous slide. So we have this summation. Now assuming the infinite sum of each of these terms exists, then this becomes the summation of all these terms along diagonal. And then all the other terms you will be summing over 0, so which is just 0. Okay, so this is sum with lambda 1 here, and this is the same summation with lambda 2, and this is the same summation with lambda n. And then we see that this summation here, if it exists, is exactly e to the power lambda 1, and this will be e to the lambda 2, and this will be e to the lambda n. So we see again, for diagonal matrix, the exponential function takes a very simple form. It is also a diagonal matrix where each diagonal is the exponential of the original diagonal in the D matrix. Okay. Now let's see if we can define the square root of a diagonal matrix. So we assume now all the diagonal elements are non-negative, so we'll be dealing with real numbers. So D is the diagonal matrix where all the lambda i's are bigger than or equal to 0 for all i's. And then we form another diagonal matrix, let's call it S, where we just take square root of all the diagonal elements here. So this is a diagonal matrix as well. And then you can carry out a simple calculation, that is S times n, which is S squared. If you carry that out and you know that it becomes a diagonal matrix where all the diagonals will be squared, right? We learned that in the polynomial of a diagonal matrix. And that is exactly D. So we have this relation S squared equal D. And then because of this relation between them, then we will call this S the square root of the matrix D. Once we have understood how to define these functions for diagonal matrices, and then the next step will be, what if the A is now a general matrix? So that's a lot trickier. So we can define these functions for some cases of A matrix. So we need to assume that A here can be diagonalized by some invertible matrix, let's call it Q. So if you multiply A on the left by Q inverse and on the right by Q, you would get a diagonal matrix. Let's say this is the lambda 1, lambda 2 along the diagonal, the same diagonal we always denoted. And then this means that with this identity, you can multiply on the left by Q. So you have Q times D, and that becomes identity. And multiply on the right by Q inverse, then you get identity here, and then you get D times Q inverse. And then you have A equal Q times D times Q inverse. So we have an expression for this matrix A. And now we can work out the power of this matrix A. A to the power k would be this term multiply itself k times. So we write them out like that, k times. And then let's look at two neighboring terms. We will have q inverse times q, and that will give us identity, so we can drop. And again, q inverse times q, that's an identity, we can drop. So every two neighboring of this expression of A, you will find the q inverse and the q. So they're all identity. So what remains in the middle would be just d to the power k, and then you have the first q comes here, and then the last q inverse, which you have to keep. Okay, so a to the power k now carries a simpler expression than this big thing. It's q d to the k times q inverse, where the D is a diagonal matrix, and we know a lot about how to handle that one. Now we are ready to derive the formula to compute polynomial function p of A. And the key identity is what we derived previous page. A to the power k is q times d to the k times q inverse. Consider any polynomial p of t like this. We can write it out for the matrix A. P of A would be summation of this with a to the k. Now we put in the expression for a to the power k, this one here. We put it in here. And then we see that in this summation here, ck, dk depend on k, but q and q inverse does not depend on k. So we could move the q to the front and q inverse to the end and take them outside the summation sign. So we can sum over ck, dk. These have the index k on it. And then we see that the summation in the middle is exactly the polynomial of D, which is the diagonal matrix. And this we already know how to do it in the previous slides. A similar idea can be applied to derive a formula of computing exponential function e to the power a. Again, we use this identity. So the exponential of a, e to the a, is this summation of this expression, a to the power k over k factorial. And then we can substitute a to the power k by our key identity. Okay, so then we put it in there. And then here we see that q and the q inverse are constant with respect to k. They don't depend on k. The term that depends on k is d to the power k over k factorial. So we can move the q and the q inverse outside the summation sign. So that's how it would look like after we move the q out on the left and the q inverse out on the right, and then we have this summation over k. And we see that this summation here we derived earlier is exactly the exponential of this diagonal matrix D, and we know how to write out that. And then you have q on the left and q inverse on the right, and that will be the exponential of A. To define the square root of a matrix, we need to put some further assumptions on the matrix. The matrix A needs to be a positive, semi-definite, and symmetric. This means that all the eigenvalues of the matrix are non-negative and A is also symmetric. And in this case, then we know we can write A as q times d times q inverse. And the q here will be some orthogonal matrix. And then the d is a diagonal matrix where on the diagonal we have all the eigenvalues of A. Now recall that the matrix S, which carries square root of lambda 1, square root of lambda 2, and square root of lambda n along the diagonal, satisfies the relation that S squared equals D. And now we define a matrix. We call the matrix B, which is Q times S times Q inverse. Okay, where S is here, and the Q's are the matrix that will diagonalize the A matrix. And then we want to verify if this B is a good candidate for the square root of A. We can compute B squared, and we want to show that B squared equals A. So let's put B here, and let's put B here. So B times B. And then we see Q inverse times Q is identity, so it's gone. And then I have S times S is S squared. So I have Q, S squared, Q inverse. And then S squared here is just the matrix D, so we get that. And then we see that this exactly gives us A, because Q is the matrix, the orthogonal matrix that diagonalizes the A. So we have shown that now B squared equals A, and therefore we call B the square root of A. We now take some examples. First example, we will compute the exponential of a matrix A. The A is this matrix, it's a 2 by 2 matrix, and we want to compute E of A. So we know that step 1 is to diagonalize A, and there you need to find the eigenvalues and the eigenvectors. So you carry out the normal computation to find the eigenvalues, find the characteristic polynomial, and find the roots of it, and you get two eigenvalues, lambda 1, lambda 2, and then you carry out the procedure to find the two eigenvectors. And then you can form the Q matrix by collecting the two eigenvectors, and then you will have the inverse of Q, which you can work out. So all that work is now enable you to represent A matrix in the following way. A will be Q times D times Q inverse, where the D is a diagonal matrix with a lambda 1 and lambda 2. And then we know that exponential of the diagonal matrix is just a diagonal matrix where the exponential is taken on the diagonal. And therefore, the exponential of A is just Q times e to the D times Q inverse. And we can put in all the numbers we have here. The Q matrix is here, e to the D is here, and then Q inverse is here. So you can work out this matrix product, three of them, and write out an expression if you want. Another example is to compute the square root of a symmetric matrix A here. So we need to check that this is positive definite, and then we want to compute the square root. So again, one needs to diagonalize A, and we need to find the eigenvalues and the eigenvectors. So I'll skip the detail, and let's say we have found them. These are the two eigenvalues, and these are the two eigenvectors, and we further normalize them so that the norm of both are 1. So these two vectors, they both have length 1, unit length. So we see eigenvalues are strictly positive, and they are also distinct, and so A is positive definite. And now we can form the Q matrix, which is collecting the two eigenvectors, V1 and V2, put here. And then we know that these two vectors are orthogonal to each other, and then the Q inverse is just Q transpose, and one can immediately write it out. Okay, so let's keep these two here at the top of the slide as we continue. So now we have this representation of the A matrix, which will equal to Q times D times Q inverse or Q transpose, where D is this matrix with the two eigenvalues. Now we can form the square root of D by taking square root of the diagonal elements, and we get that. And then with this, we can form a matrix B, which is Q times square root of D times Q inverse. And then here we can put it in all the numbers that we have. So this one times this one is 1 over 5. And then we have this matrix is Q, and this one for Q inverse, and then this one for square root of D. And this B here will be the square root of A, because you can easily go and verify that B squared equals A. So that's the end of this example and the end of this lecture. Next time we'll be applying all the knowledge we have here to derive and to understand one important algorithm called singular value decomposition, and furthermore its application into many things. So I hope you enjoy this lecture, and I'll see you next time.